Vi redo? All right. Okay. In the next chapter, we're going to be talking about Ethernet and an overview of Ethernet. So Ethernet, what it used to be, what it is now. We're going to talk about 10 megabit Ethernet and fast Ethernet or 100 megabits Ethernet. We're going to look at some connectivity options, different cables, stuff like that. We're going to look at some different Ethernet frames. One of them is the Ethernet version 2 frame. We're going to look at straight through and crossover Ethernet cables, see why we have them and what they're used for. And then I won't go into the 10 and 100 megabit Ethernet design rules, because those rules are design rules for hubbed networks. And since we're not running hubbed networks, learning you about the design rules for 10 and 100 megabit hub networks is a waste of time and a waste of memory space for your own mind. So we'll skip that. We'll talk a little bit about gigabit Ethernet. So Ethernet, which is today, as I said, the LAN technology for wired networks. If you have a wired networks, 99-point-something% of them are Ethernets. Ethernet started out in the early 70s, as you can see, with 3 big companies, Digital, Intel, and Xerox. It is therefore also still today some places called DICS Ethernet. Now, DICS Ethernet were, to begin with, 1 or 2 megabit Ethernets. DICS Ethernet 2 in 77 is Ethernet 10 megabit Ethernet, what we usually refer to. If you only say Ethernet, you used to refer to 10 megabit Ethernet back in the old days. And then came along the 100 megabit Ethernet, which we called fast Ethernet because it was really fast back then. And then we got gigabit Ethernet and 10 gigabit Ethernet as well. There are different frame formats between the DICS Ethernet or the Ethernet 2 frame and the one that was standardized by IEEE. The standard, IEEE standard, is called 802.3. And there's a difference. Now, as a user, and also most time as a network administrator, you don't have to care about the different frame types. They look more or less the same. The switches, hubs, and routers don't really care what kind of Ethernet frame it is. So I won't go into a big deal about the different frame types, but you should know that there are different frame types. Today we usually talk about 4 different frame types. One is the Ethernet 2 frame type, and then the IEEE 802.3. There are 3 different frames. I won't go much into the detail, but that's what it is. Ethernet is using something called CSMA-CD, stands for Carrier Sense Multiple Access with Collision Detection, and we'll go through that algorithm and see how Ethernet works with that. Yes.
You have 2 Ethernet versions. Are they treated as 2 separate networks?
No. It's the same. And the Ethernet switches, hubs, and routers today, they can handle both types or 4 types of Ethernet frames. So the only time that I know about you having to know about the different frames is if you're running network clients. At least back in the days, you had to tell the network client and the network server what kind of frame type it was supposed to use. Other than that, it's not something you talk about. People say, I'm running Ethernet. And if you put a protocol analyzer, a sniffer, on your network, you're going to see that most of the frames are Ethernet 2 types of frames. Some of them are IEEE frames, but it really doesn't matter. Some protocols is using one frame and another protocols are using the other frame. From a user and a network administrator perspective, you you basically never care about it. It's just something you should know. Obviously, to get your computer connected to the network, we need a network interface card, or a NIC, nätverkskort. It has to be, obviously, if it is Ethernet, you're running an Ethernet network card. You can't be running token ring network card if you're supposed to be connected to an Ethernet. All network cards have a media access control, or MAC address. Now, the MAC address is the layer 2 address. The MAC address is made up by two parts. The first 3 bytes is the vendor ID. By looking at the first 3 bytes of a MAC address, I can say what vendor created it. So if Cisco, for instance, is creating network cards or router or a switch and it needs a MAC address, Cisco is going to use one of its, and they have like 20 different 3 bytes codes. It's going to use one of them. If Nortel or Ericsson or any other company creates something that needs a layer 2 address, a MAC address, you're going to use your MAC address. That vendor code is also called the OUI, the Organizational Unique Identifier. So by looking at the first 3 bytes, I can know which manufacturer have created that MAC address.
The MAC address is a
It's static, yeah. Today, you can change the MAC address. There are drivers for some network cards where you're allowed to go in and change your MAC address. Very seldom any good reasons for doing that. You don't have to. It's just the later part, the last 3 bytes of the MAC address is usually, it's vendor specific, but it's usually serial, just a serial number. Now, if you think about that, if all of the vendors, all of the manufacturers only use their own vendor codes and they keep track of their own serial number and don't reuse the serial numbers, it will mean that we have unique MAC addresses, right? And that's what we're supposed to have. Now, there are some companies, most of them from an island outside of China, that don't care about all of these things. So you could end up with duplicate MAC addresses. Also, there could be manufacturers that say, well, we created this series of this serial number. We used that for network cards from 15 years ago. Now, the possibility or the chance or risk of it having the same as something that is used today, if it were created 15 years ago, is very slim, so we'll reuse it. But you shouldn't have duplicate MAC address because of how the MAC address is built up. It also means that on a given network, there's no way for me to look at the MAC address and say, well, that MAC address, well, you're supposed to be on that network over there. And this MAC address, you're supposed to be on the network over there. Because there could be different kinds of MAC addresses. Obviously, on the network, you had PCs with network cards from Sercom, Nortel, and different kinds of manufacturers. They can all be on the same network, obviously. So MAC addresses are using what they call a flat address space. So just everyone has one. It doesn't have to be the same or looking the same. Just have to have one. The MAC addresses are used for sending Ethernet frames. So that's the addresses we use to send Ethernet frames on the Ethernet network. Different operation systems. If you're running Windows, for instance, you could buy a network card from different manufacturers. Now you need to tell Windows how that network card is supposed to work. How do I send data? How does that network card send data to me? And to be able to talk between the operation system and the hardware, we have drivers. And obviously, we also have drivers for the network cards. Drivers are software pieces that the manufacturer creates to let the operation system know how the hardware is working and vice versa. So obviously, we're going to need drivers. Same as you have graphical drivers and sound card drivers and all of that to make sure that the hardware can function with the operation system. Now, Ethernet works by using the algorithm CSMACD. It stands for Carrier Sense, meaning that before I can send data on an Ethernet, I will listen to the wire. Carrier Sense. So if I'm supposed to send something, I'll listen. And it's only if the wire is quiet that I'm allowed to send data. So I will listen for the wire, and if no one else is sending data, I can then send data. If someone else is sending data already, I'll have to wait. So that's the carrier sense part. The MA stands for multiple access. And we're sharing the bandwidth, so we got multiple access. There are lots of different host devices on the network, and we're sharing the network. So we got multiple access on the network. And the final part is the collision detection. Now, if we are two or more PCs or devices on the network, there might be a collision. If there is a collision, we need to detect that. So the collision detection says that if two devices start sending at the same time, the signal obviously is going to overlap. We're going to have a collision, and we need to notice this. So the collision detection part is noticing collisions. When that happens, the network cards will send out a jabber signal, small signal saying to everyone, we had a collision, and then the ones involved in this collision will do a back-off algorithm. They will back off. They have to be quiet for a certain number of microseconds, and then we'll add a little random number to that, making sure that they don't back off exactly the same time and then try to send again at the same time, because we're going to have a new collision, right? So we'll back off for a certain number of microseconds, and then we'll add a little random number to that. Now, once I've backed off, I can then do the carrier sense part again. Listen, if no one else is sending, I can then start sending. So carrier sense multiple access collision detection means that Ethernet is contention based. The more users on a network, the less data you're going to be able to send. How much data? I don't know. It depends on what the other PCs, the other things on the network is doing, how much data they're sending and when they're sending it. Now that's the way it used to be. It's not that bad today. So in this case, I think it's A is want to send some data. He's going to send that data to the hub. But before he sends it, it will use carrier sense, so we'll listen. If no one else is sending data, I can then send the data. I will send the data in an Ethernet frame. I will send it to the hub. And the hub, being a hub, will send it to everyone. So every single one, B, C, D, and E, are all going to have, they're all going to receive this frame. They will receive it on the Ethernet card and will check the destination MAC address and see whether it's their own. If it is, I'll receive the frame. If it's not, I'll throw it away because it wasn't supposed to be to me. Collision domains. I'll do some drawing now. When we started out with Ethernet, and you'll see this in a couple of slides, we were all connected together on something called a bus technology, bus topology. Coax cable started out with a thick coax cable, about this thick, centimeter or two, yellow or orange usually. Anyone seen them? Quite thick cables. To connect to it, use something called a vampire tap. In Swedish, or basically it's a nail, speak. Just push it through the cable, and you connect your PC to the cable, and you'll add it like this. So we can add PCs and servers onto here. Is it too small? You all see it? Right. Now this is typical shared media. It's one cable. If I send something from here, it's going to go out on this cable and everyone's going to receive it, right? That's the way it used to be. This thick cable, thick coax cable, or thick net, the standard is called 10 base 5. And the 5 stands for 500 meter, because that's the length, the maximum length of this cable. It could be 500 meters long, no longer. This is really not used today. You might find it in factories and stuff like that, but otherwise it's not used. Now, after this, there came something called the 10 base 2. And the 10 base 2 is also coax, also copper cables, but it's the thin version. The one looking like the antenna for your TV antenna coax cable. So you got that white cable, and instead of using the vampire tap, we use something called the BNC. It's contact looking like this with connections on the side. Anyone seen those? It looks the same on a topology. As a topology, it's still the same. You still connect your PCs to that coax cable, not using the vampire tap, using this connection now. Still shared media. If I send something out here, obviously it's going to go all over the area within 10 base 5 and 10 base 2. Now, if this isn't far enough, if I need to go 10 base 2, by the way, stands for 200 meters, close enough because it's 185. Now they couldn't call the standard 10 base 185, so they called it 10 base 2, about 200 meters. Now, if 200 meters or 500 meters isn't enough, what do we do? What did we do? We added a repeater. So if I add a repeater here, I can add another 500 meters or 200 meters. And I can still put new PCs and stuff on here, service and stuff. Now the repeater is a layer 1 device. So the only thing it will do is it will repeat any signal. So if this signal coming in here is going to be repeated out on the other side. Now in this kind of environment, because we're sharing the topology, because we're sharing this bandwidth, there's only one at a time that can send data. And every single one on the network is going to receive everything that everyone sends. If two devices start sending at the same time, we're going to have a collision, the frames is going to be corrupted, and we're going to do the backoff algorithm, and we'll redo the transmission once we waited. All right? This area, where there is, because we're sharing the bandwidth, only one at a time sending data, that area has a name, and it's called the collision domain. Collision domain is then this area, all of it. One at a time sends data. Now, we talked earlier, we said the Ethernet were called 10 base T, right? Remember that? Now 10 base T is a 10 megabit Ethernet, obviously, but using twisted pair. So instead of having this, what we have is a hub in the middle and twisted pair cables out like this to your PCs. Now the hub is also, same as the repeater, a layer 1 device. So if I send something from this PC to the hub is going to send that frame out to everyone. So this is still a collision domain. It's one collision domain, one at a time can send data. If there are two sending data, they're both going to send it to the hub, and the hub is going to send both of the signals out to the others, and we'll have collisions. All right? That's the way Ethernet used to be. But then something came along called a, anyone know? Bridge. So I'll add a bridge up here. And the bridge, because it's a layer 2 equipment, a layer 2 device, a bridge understands the Ethernet frames we talked about. The frames is a layer 2 frame, remember? The bridge understands frames. He can go into the frames and he can find out which MAC addresses are on this side and which MAC addresses are on this side. And it's only if it needs to go from here to here that I will send it from here to here. If it's going from here to here, I don't need to send it out here, right? So the bridge won't do it. I will only send data if it needs to go to the other side. And also, I got buffers. So if I'm sending data from here to here, no one's sending data on this collision domain because there's another collision domain on this side. If no one is sending data on this collision domain, I can send data. So I'll send it to this server. It will go to the bridge, and the bridge will buffer it. And if we find out that to go to this MAC address, I need to send it out on this port. Now, if it's occupied, if someone is using this collision domain, I will buffer it, and I will send it when there's opportunity for me to send it. So I will split this LAN into 2 different collision domains using a bridge. You okay with that? Now, all of this together, so anything connected with hubs, making it the same collision domain, or if it connected with hubs and or bridges, is called a broadcast domain. Because if I broadcast something, it will go out to all. You know that in Datacom, we're talking about 3 different costs. We're talking about the unicast, which is from 1 to 1, from me to you, from one PC to a server, from a single PC to a router or whatever. It's unicast from 1 to 1. We're talking about broadcasts, which is from 1 to everyone. And there's certain protocols, one which we'll talk about in a while, that needs to broadcast data. And there's a multicast. And the multicast is from 1 to whoever is listening to that multicast address. For instance, 2 routers sending traffic between each other might be using a routing protocol called RIP or some other routing protocol. There's a multicast address for routers using RIP. So I can multicast something on that multicast address, and if I'm interested in RIP updates, if I am a router and I want that RIP updates, I'll listen to it. If I'm not, I'll throw it away because I'm not interested. So we got unicasts, broadcasts, and multicasts. The broadcast domain, if I'm broadcasting something, I want everyone to have it, right? That's why I'm broadcasting it. So by broadcasting it, the bridge will send it to the other side. Okay? Now, same that happens with repeaters. Repeaters started out by having 2 ports, 1 on each side. And I will repeat anything that comes in on one port and I'll send it out on the other one. And then they created multi-port repeaters. And some management or some marketing people said, well, we can't call it a multi-port repeater. Let's call it something else. And they called it a hub. A hub is a multi-port repeater. It is still a layer 1 equipment, layer 1 device. Repeater and hub, same thing, different name, multi-port repeater. Same as the bridge. The bridge, starting out by bridging one collision domain with another. Bridge had 2 ports. Now they've created multi-port bridges, and we can't call them multi-port bridges, so we call them switches. Now there's more to the difference between a bridge and a switch. But today, we're not talking about bridges anymore. We're talking about switches. So if I add the switch is gonna, the same way as the bridge does, is gonna stop the collision domain. On the other side of the switch, we're gonna have another collision domain. Now that collision domain could be connected to another hub, meaning that this would be, obviously, another collision domain. But it could also be connected directly to a server, in which case this switch and the server has its own little collision domain. And I'll get back to that in a minute, because that collision domain is what we usually have today, and it's very useful. So we'll get back to that. Obviously, all of this still is the same broadcast domain. Same thing as we had previously. If you connect it to a repeater or a hub, you're on the same collision domain. If you connect hubs and or bridges or switches together, they're all connected in the broadcast domain. Now the broadcast domain is interesting because the broadcast domain is what we call the LAN. The definition of a local area network is that it is a broadcast domain. That's the definition of a LAN. Anyone know of a kind of device that throws away broadcast, that is, stops the LAN or stops the broadcast domain? The router. So if I add a router on here, for instance here, the router is going to stop the broadcast domain. The router throws away by default all broadcasts. I'll get back to that later, but you can remember the router stops the broadcast. And therefore it also stops the broadcast domain. On the other side of the router, there might be another switch with hubs or PCs connected to it. Or there might be a WAN link running PPP or some other WAN protocol, WAN link. But it is the router that stops or ends the broadcast domain and ends the LAN. All right? So Ethernet collision domains, if you go back 15 years, you had companies, big companies, running hub networks. Everything hubbed. Everything, all the same collision domains. Perhaps a couple of collision domains. Lots of users on the same collision domains. Now, if you understand what happens with collision domains and only one at a time sending data, you can see that this is not very efficient. So what we do is we'll put switches in, and we'll create smaller collision domains. So instead of having all users on the same collision domain, we use switches to create smaller collision domains. And this is what it used to look like perhaps 10 years ago, between 10 and 15 years ago today, early 90s, or mid-90s perhaps even. Hub networks, collision domains, and then switches every now and then to split this up into smaller collision domains. If you have a server, high capacity that lots of users using, it might have been on its own collision domain. If you're a super user or a guy that is a buddy with the network administrator, you might have your own collision domain, depending on what kind of applications you're using, perhaps. You okay with collision domain, broadcast domains? Right. I won't go much into the different kinds of Ethernet, but on this slide, on this page rather, And we're now on page 512. You can see some different standards for Ethernet. The first number tells you the speed in megabits, so 10 megabits obviously. The base is baseband. Baseband basically means we're sending one signal on the cable. As opposed to broadband, we have different kinds of technologies to be sending different signals, more than one signal at a time. Easiest broadband is your cable TV or your TV cable. You got one cable coming in. On that cable is lots of signals. They're all frequency division multiplexed to allow us to have more than one channel on that one cable. Now baseband is one signal. The whole signal takes the whole cable. I'm just sending one signal on there. And the final part, in this case the T, stands for the media. In this case it's twisted pair. So the media we're using. So UTP cable. Another example, gigabit Ethernet, 1000 megabits then, still using baseband, and in this case it's short wave laser or light. The X, as you can see, is in some standards, stands for full duplex, which means that it's capable of running full duplex. And I get back to half and full duplex in just a minute. Remember we talked about the Ethernet frames, and I said there are 4 different frames. One of the most common ones is the Ethernet 2 frames. The Ethernet 2 or Dixie Ethernet frame has this, looks like this. It's got a, you don't usually talk about this part, the preamble and the starter frame delimiter. Now the preamble or starter frame delimiter is there for synchronization reasons. On an Ethernet, as opposed to most of the synchronous interfaces, there is no synchronization signal. And whereas the PC has a network card, and that network card has a clock, and 10 megabit Ethernet means I'm supposed to send 10 million bits per second, right? You can taste that for a minute. 10 million bits in a second. Now, even though we have a clock, that clock is not necessarily going exactly the same. And if I'm supposed to send a frame consisting of an Ethernet frame, could be 1,500 bytes of data. If I'm sending a frame that big, that much data, and the receiver and the transmitter's clocks are slightly off, somewhere in the middle of that frame or in the beginning of that frame, depending on how much off we are, we're going to lose synchronization. And the frame is going to be corrupted. Because there's no signal synchronizing on the network, we'll use the preamble or start frame delimiter to let the receivers of the signal synchronize on the transmitters and his clock. So what the preamble or start frame delimiter is, it's just the bit patterns. 10, 10, 10, 10, 7 bytes. That's the preamble. And the start frame delimiter is 10, 10, 10, 11. The final one tells the receiving station that the next bit is the first bit in the actual frame, in the actual data. So that first 8 bytes is there for synchronization purposes, to let the receiving station synchronize his clock with the transmitting station. And this is done on every single Ethernet frame, always. It's very seldom, though, you will never see me draw an Ethernet frame with a preamble and start frame delimiter, because it's not data, it's just for synchronization. So usually when you draw those frames, the preamble and start frame delimiter isn't there. It's going to be replaced with a new preamble and start frame delimiter when I send it out, looking the same, but based on my clock, the one sending it. So it's synchronization purposes. The actual frame then is the destination MAC address, and because it's a MAC address, it's 6 bytes big. So whoever is supposed to get it, that MAC address. Then there's a source MAC address, so my MAC address. Notice that the source MAC address is always my MAC address. It cannot be anything else. It has to be my MAC address, the sending station's MAC address. The destination address could be a unicast address if it's supposed to go to a specific device. It could be a multicast address if it's supposed to be a specific multicast address that more than one station might be listening to. Or it could be the broadcast address. The source address is always my own address. It has to be my address. It cannot be any other kind of address. It's the unicast address, the sending station's MAC address. And if this is an Ethernet 2 frame, it will be a type field. Now the type field is a 2-byte field, and it will let me know what's going inside the Ethernet frame. So what the Ethernet is carrying. If this inside here, this data part, if that's an IP packet, the type field here is going to be 0800. It's the type code for IP. If this inside is an IPX packet, the type code will be 8137. And if there's another protocol, there will be another type field. So the type field will let me know what's going inside the frame. The data part of an Ethernet frame is between 46 bytes, has to be at least 46 bytes. If the data you're sending isn't 46 bytes big, we'll have to add padding. It has to be at least 46 bytes big. If it's smaller than that, we need to add padding to make it 46 bytes. And the maximum frame size is 1500 bytes. And at the end, we'll add 4 bytes of frame check sequence. A checksum to make sure that this frame is complete. So when I'm sending it, I will take all the parts from the first bit in the destination address to the last bit in the data packet, in the data part. I'll run it through an algorithm, and whatever the result is, I will add that to the end of the frame as a checksum. When I receive it, I will take the data received, run the same algorithm, and I will check the result I get with whatever is sent with the frame. If it's the same frame. It's complete. It's not been altered. There's no errors on it, so I'll receive it. If it's not the same, it's corrupt, I'll throw it away.
Who administrates the MAC multicast addresses? Are there a number of predefined?
Yes. Yes. We're interested in IP, right? To start out with, the MAC address, I don't know if this is on the slide, but the MAC address in the first byte of the MAC address, the least significant bit in the first byte, the bit meaning 0 or 1. If that bit is set, it's a multicast address. The only exception to that is if the other 47 bits is also set to 1, so all 48 bits is set to 1. Because if all 48 bits is set to 1, it's the broadcast address. It's one broadcast address, all bits set to 1. If it's not the broadcast address, but the least significant bit in the first byte is set, in that case it's a multicast address. IP multicast, because IP is using multicast as well as Ethernet is doing. So an IP multicast address always starts with an IP multicast address always starts with 01. This 1 is the least significant bit in the first byte, right? This is the hex for first byte. So this is a multicast address, 005E. All IP multicasts always start with this 3-byte code. The first 3 bytes is always this. The IP multicast, for instance, 224009, which is used for RIP version 2, it's the routing protocol. This IP multicast is going to be translated in Ethernet to 01005E because it's an IP multicast. And then I'll take the final 23 bits. 23 bits is kind of funny because it has to do with money. When they did this IP-wise, you have to buy these 3 bytes codes. And they were expensive. So when they did this, the guy doing multicast and IP said, I need 24 bits so I can map the IP addresses down into MAC addresses. So I'll need 24 bits. And the one sitting on the money said, nope, you're going to have 23 bits. And the one bit we're going to use is the one where this is set to 0. The final first bit here, the 24th bit. So these 23 bits will map directly down to these 3 bytes, or rather, the first one is going to be 0. So this is going to be 000009. This is the layer 2 multicast address for this IP multicast address. Did you understand the bit part? If you didn't, we'll go through it later. Basically, because you don't care about this IP address, part of the IP address, and you don't care about the first bit here. So the layer 2 multicast address for 239.128.0.9 is the same. Because I don't care about that first bit. Well, you're familiar with bit counting. You know that the bits in the byte has these values. This one is the least significant bit, right? This one is the most significant bit. Now, in this byte, we don't care about the value of this because we only have 23 bits. This one isn't part of it. So whatever this bit is on layer 2, it's still going to be 0. So whether it's 0, so it's all zeros here, or whether it's 128, so this bit is sit, can't see that on layer 2. Because we don't care about this bit if it's in this byte. So it will all be mapped. And since we don't care about this at all, it doesn't matter what multicast address it is on the first byte. It will all be mapped into this anyway. All right? Answer? You okay? Yeah? Right. And as I already told you, the ether type is what tells me what's inside the Ethernet frame. So if it's an IP packet, as on the slide, it will say 0800. It will let me know what's inside. If you turn your page, on page 516, you can see that there are some other type codes there for different things. Now, IEEE then made a standard, and the IEEE frame still contains the preamble and the start frame delimiter for synchronization part, synchronization reasons. We still have a destination address and a source address, still MAC addresses, same order, same size, still MAC addresses. But instead of the type field in the IEEE frames, there's a length field. So instead of having a type field, there's a length field. Now the length field is telling me not what this is, it's telling me how long it is, how much data is inside the Ethernet frame. So you can see whether it's a IEEE frame, because it has a length field, and you can see if it's an Ethernet 2 frame, because it has a type field. They're both 2 bytes big. Now, if there's a number here, a 2-byte number, how do I know whether that 2-byte number is a type field or a length field? How do I know by looking at the number whether it's a type field or a length field? Well, they were kind of intelligent when they did this. The length field can only be 1500 bytes, right? the maximum length of the Ethernet frame can't be any bigger. So the length field can only be 1500 bytes, 05 DC in hex. Now all type fields are bigger than 1500 byte decimal, or they're bigger than 0600 hexadecimal, sorry. So by looking at the size of the number, if it's smaller than 0600 hex, it's the type field, length field. If it's bigger, it's the type field. And then there's the actual packet. Now, some of the Ethernet frames from IEEE has a logical link control field used to do flow control on layer 2. IP does not use it. This is a protocol analyzer. Has anyone been working with the protocol analyzer? Really funny to look at, because you can actually see that whatever I'm talking about, whatever I'm telling you, you can actually see it actually works. When I go to a seminar or listen to an instructor or read something in a book, sometimes people say one thing and I read something else. One instructor or guy says one thing and another one says another thing. How do I know which one is right? Well, I put the network up, I put the sniffer in between, the protocol analyzer in between, and I create the traffic. And I'll look at the traffic and I will see which one is lying. So the protocol analyzer basically, I'm not going into it, but you got a detailed view where the protocol analyzer has decoded the frame. And you can see all the different fields that I've been talking about, and there's an IP header which we'll go through later on as well. In this case, it's an ICMP message, which we'll go through in the afternoon as well. So this is the decoded version of the frame. In the bottom, there's a hex ASCII code from how the frame looks when it goes on the wire. And this one is the ASCII representation of the data. So, for instance, if you're running Telnet or something, one of the problems with Telnet is that it's not encrypted. So if it's not encrypted, I will send the user password in clear text. Now, if I get a sniffer, that name, my username and the password will show up here in clear text because it's just not encrypted. So I can see it with a sniffer. So any text, any ASCII text, is going to show up on this part. There's a really good free sniffer protocol analyzer. It's called EtherReal. EtherReal. So if you look at it on the internet, Google for it, for instance, I think it's www.etherreal.com. I think it could be org as well. EtherReal with one R. It's a freeware and it's really good. Doesn't look as fancy as the ones you're buying, but it's free. Ethernet equipment. Obviously, your PC is going to have a network interface card. You can have hubs, switches, and routers. Hubs, layer 1, switches, layer 2, router, layer 3, and above. Layer 3 at least. Difference connectors, we talked about those previously. Back in the time where you had both thick Ethernet, that 10 base 5 and 10 base 2, and then started to have 10 base T kind of networks, it was useful for the equipment to have a AUI. This is used for connecting a transceiver, and depending on what kind of media you have, you can connect that media. So even if you have a thick net, or if you have thin net, that 10 base 2, or if you have 10 base T, you could have different transceivers, and you connect it to the equipment using that AUI interface. The BNC, we talked about that. The usual UTP cable has an RG45 connection. So that's the one you put into your PC. It's called an RG45. There are different kinds of fiber connections. Straight tip, square connector, and there's something called a small form for making the connector smaller. All right. Time for some drawing again. There are different kinds of pinouts on the PCs and switches and hubs and routers. And if you connect something together, do we need a break? All right, let's take a 10-minute break now before we start out on this, because otherwise we'll take 15, 20 minutes more. So let's have a break and then we'll go through the cabling when we get back.